I think we can start. Can you hear me fine? I guess so.
Yes.
So,
Yes.
good afternoon, ladies and gentlemen, and thanks for joining this lunchtime seminar organized by Young SECED members. The topic of today is Tsunami Engineering, which will be discussed by Professor Tiziana Rossetto, notably known for being Professor of Earthquake Engineering at UCL, co-director of Epicenter, the interdisciplinary center for multi-hazard resilience, but also for being one of the leading experts in the topic of tsunami engineering, having led work on advancing structural analysis methods for tsunami. Together with her, we have Dr. Marco Baiguera, a research fellow at the Department of Civil, Environmental and Geomatic Engineering, who joined the Tsunami Engineering Research Group in 2018 and worked ever since on the development of innovative tools for the assessment of building to tsunami, and is also a member of Young SECED Group, and Dr. Marta del Zoppo, a research fellow in the Department of Structures for Engineering and Architecture at the University of Naples, Federico II. Since 2018, she has been working on the performance and vulnerability assessment of existing structures for tsunami loading. In 2019, she joined Epicenter, collaborating with Professor Rossetto and a research group. The presentation of today is divided into three parts. So Professor Rossetto will start with her introduction on the topic of tsunami engineering. Marco will follow with his presentation entitled A Procedure for Performing Nonlinear Pushover Analysis for Tsunami Loading to ASHE-7. And then Marta will follow with a presentation entitled A Methodology for the Performance Assessment of Existing Frame Structures under Tsunami Loading. Before leaving the stage to the speakers, I want to remind you that we are currently recording this seminar, so please keep your microphone muted. Please keep your questions to the end, at the end of the presentation, and share them via the chat box so that I can read them aloud and the speakers can answer. Thank you very much. I'll now leave the stage to Professor Rossetto.
Thank you. Valentina, you're going to have to give me an instruction on how to share my screen because I can't find the sharing button.
So it should be more action.
Yeah.
And then share your screen.
It's not there. Maybe disabled sharing?
Should be on the top right, near the leave button.
There's share content.
Yes. Yeah.
Order, yeah.
Aha, fantastic. Okay, can you see my screen?
Yes.
Okay, hang on. You're able to see the presentation? Yes? Okay, apologies for my incompetence in terms of technology. Thank you for being with us this lunchtime. I'm Tiziana Rossetto. Thank you very much, Valentina, for the wonderful introduction. I'm going to share with you just an introduction to tsunami engineering, which I've been working in now since the tsunami that hit the Indian Ocean, that occurred in the Indian Ocean in 2004. Some of you may not realize, but there have been more than 2,000 events since, well, recorded in history of tsunami. So they are very rare events, but there have been significant ones, and particularly when they happen, they can cause significant destruction, life and economic loss. One of the most expensive disaster worldwide is actually the Tohoku earthquake and tsunami that happened in 2011. The work that is presented today is part of research that I've been conducting for the last 13 years with a number of partners. So I thought I would list these here to start with to show that this is not just one or two people's work, but actually is the work that Marta and Marco are presenting. All of that has been led up to by significant collaboration with many partners across UCL, as well as outside of UCL, HR Wallingford, etc. But let's start on our journey through tsunami engineering. And let's start with just the first question, which is, what does tsunami look like? So for those who don't know, a tsunami is essentially a large wave, and it has particular characteristics. When it's offshore, in deep ocean, it typically has quite a small amplitude, and when it comes near shore, the amplitude grows and can devastate, can cause quite a lot of damage. So this is a picture from the Fukushima Daiichi nuclear plant in Japan being hit by the 2011 tsunami, and it's showing that the seawall, for example, is being damaged. But a particular feature of tsunami compared to other waves is their wavelength. So they are extremely long, and this is important. This is important from the point of view of the inundation properties as well as their forces on structures. So we're focusing on the tsunami or the structural engineering part of tsunami today. But the characteristics of the tsunami have an important influence on the loading that the structure feels. So this is just showing you a picture of the Boxing Day tsunami as measured by an echo sounder offshore of Thailand. And it shows that the wave period is about 23 minutes. And this is offshore. This long wavelength results in a very long duration inundation onshore. So we're talking flows that last a matter of minutes, not seconds. This long duration inundation therefore also results in what we now know is a quasi-static loading on coastal structures. And it's worth remembering that because many of you are earthquake engineers and we're not used to thinking about static loads so much as dynamic loads. And I think quite a revelation to myself as well was actually that in the case of tsunami, buildings, their dynamic properties are actually not excited. And within the this image, what I'm trying to show you is a set of curves for a single degree of freedom system, or a series of single degree of freedom systems with different ductility levels shown in the different colors. And it's basically looking at what overstrength can these single degree of freedom systems, which have elastoplastic properties, what overstrength can they achieve when they are affected by loading that lasts T duration as compared to their period. And looking at the curves can be quite difficult to interpret. So I'm going to give you an example of what does this mean in practical terms. If we think of a 10-story building which has maybe a natural period of around 1 second, and let's say it has a ductility of 4, if you look on the curve, essentially its overstrength will be about 0 for any load that exceeds a duration of 3.5 seconds. It's not exactly just the load duration, but the load, a load greater than its yield strength. So as a tsunami load can exceed 20 minutes, then really the ductility plays a very little role. In earthquake engineering, we use ductility to resist for short period loading, for very short period loading, higher loads than the yield strength of the structure, or higher loads than actually the maximum capacity of the structure. And we take that through deformation, and that deformation is then recoverable typically after an event. In the case of a tsunami, no, your structure yields, and then the loading keeps pushing it. So it keeps deforming the structure until the structure collapses. And this is a major difference between the two types of loading. And I think it's a difference that has been largely overlooked because tsunami engineering has been led by earthquake engineers. So, so what are the other differences between earthquake loading and tsunami loading? Well, quite simply, the distribution of loads. So if we think about a nonlinear static approach that is often used in earthquake engineering, you apply the loads in an inverted triangle, like as shown here. In the case of tsunami, the loads come from below. Essentially, the water inundates the ground story, first story, third story in sequence, and therefore the loading is applied from below in a triangular approach. Now, if we push over the structures using these two different loading distributions, we actually see very different loading capacity, strength capacity of the structures. So under the earthquake loading, the seismic strength is actually much smaller than the tsunami strength. And this is something that is also quite interesting. So there is no direct relationship between earthquake capacity of a structure and the tsunami capacity of a structure. And this is something that Marco will come to again within his presentation. So the two main differences between earthquake responsive structures and tsunami responsive structures are given by the nature of the loading, the fact that the loading comes from below, and the fact that the loading is long duration, and therefore that ductility essentially plays no role. So a tsunami response is dominated by the strength of the building, purely by its strength, with no contribution of ductility. Tsunami loading also, because it comes from below, it applies massive shear forces, lateral shear forces on the elements, particularly at the ground story. And again, this is something that you will see both in Marco and Marta's presentation. But because it's long duration loading, nonlinear static methods can actually represent the tsunami response of a structure well, and much better than they can in an earthquake situation, because earthquake is actually a very strongly dynamic loading in actually a tsunami, and we simulate, we assume it's static when we're applying pushover methods, but actually it's not. In the case of tsunami, nonlinear static methods can represent tsunami response properly, but we cannot use the same methods that we use in earthquake engineering. So new tools need to be developed, and some of these are going to be explained by Marco. So in the next two presentations, what you're going to see is essentially a summary of some of the advances in both design and assessment of structures for tsunami carried out by our research group and collaboration. And so I hope you will enjoy. I will pass over to Marco first, and thank you all for listening to my short introduction. Marco?
Can you see my?
Yes.
Okay, great. Okay, thank you, Valentina, for your introduction, also for Tiziana for introducing the topic that I'm going to present, that is methodology for performing nonlinear static analysis for tsunami loading within the new AC7 standard. As mentioned by Tiziana, this is a collaborative project that Tiziana and I have been working with Crescenzo from Petrona from Willis Research Network, past Epicenter member, and Professor Ian Robertson, who is from University of Hawaii and has been a leading figure in the development of these tsunami design provisions. Now, the new AC716 Chapter 6 offers a comprehensive and practical methodology for the design of structure for tsunami loads and effects. This is the first, let's say, comprehensive guidelines and design code available worldwide. And these provisions apply to essential and critical facilities and tsunami evacuation structures that are located along the US coast that is vulnerable to tsunami. Although not required by these provisions, but the local communities are highly encouraged to require tsunami design for taller buildings to provide additional options for evacuation. The code provides load cases and structural acceptance criteria for the structural system and the structural components. And the checks usually follow a prescriptive approach and use of simple linear static analysis. But the code allows also for the use of performance-based methods, including the adaptation of the of nonlinear static analysis to tsunami loading. However, there is no guidance as to how these tools and these analysis tools should be performed within the context of tsunami. So the question for most of you might be, how do we perform a tsunami pushover analysis? And as Tiziana mentioned earlier, we can start definitely from the seismic pushover analysis, and that has been a typical approach in past research studies. Essentially, it's called constant depth pushover. You apply just a fixed at fixed locations the loads along the height of the structure, and you push that structure up to failure, and that assumes a constant depth. But as you may expect, this is not very realistic, because in a tsunami is an inundation, so there is an increase and decrease of the tsunami depth and flow velocity over the story, let's say, over the duration of the event. And that led to the development a few years ago at UCL of the variable depth pushover, which was found actually to capture better the effects of the tsunami on the structure. And these analyses, both the tsunami depth and the flow velocity are increased following a load control approach. And that is however, a limitation, because it cannot capture the degrading branch of the pushover curve. So more recently, we came up with an approach that is the VDPO2. It's essentially a two-phase pushover that combines the advantages of both methods. So in the first phase, we apply an increasing load in depth and flow velocity up to the point where we want to stop the analysis because we have reached a prescribed load, or because there is a numerical convergence issue. At that point, the analysis switches to a second phase. Now, the presentation today will be showing you how we try to adapt this methodology within the design framework of the AC716 to provide a tool that users and practitioners may follow when they have to design a structure to tsunami loading. Let's say, to demonstrate this approach, I will be using a case study building that is a 6-story reinforced concrete building located in a very highly exposed area to tsunami in Seaside, Oregon. This area is also adjacent to the cascaded subduction zone, so that means seismic and tsunami hazards are very high. Based on the location of the building, a user of the AC716 can estimate the maximum hazard data for the building site. So can estimate the inundation depth and the flow velocity using this freely available software and applying a energy-based approach that is provided by the code. What is important to mention here is that in using this geodatabase tool, you can identify all the locations that are vulnerable of being inundated along the US coast to a 2,500-year event. That's the maximum considered tsunami according to the code. So the code also provides a time history curve for the tsunami. So that means how the flow depth and the flow velocity are assumed to vary during the event, and that identifies some load cases that are a part of the design process. What's important here to remember is that actually these are the two main parameters that characterize the hazard at the building site. And one can estimate relatively in an easy way what's the total force applied to the structure, the overall force that will be resisted by the lateral force resisting system. And it's interesting to note that the maximum force is occurs when the flow velocity is reaches its peak, and the flow depth is 2/3 of the maximum value. This load, this stage is identified in the code as load case 2. So this is, let's say, the background in terms of design. So how do we apply all this into our pushover analysis? Well, it's clear that load case 2 is controlling the design of the structural system. So what we have come up with is to apply directly the time history, the pseudo time history analysis curves provided by the code into the analysis tool, so that we can evaluate the behavior of the structure up to this maximum force. And at that point, the analysis can switch to a constant depth pushover to bring the structure to failure. But once we know this force, the question is, how do we apply this force to the structure? Okay, the AC716 considered the tsunami force as uniformly distributed along the structure, but does not prescribe how this force should be applied along the columns when discretized. So a typical approach here in past studies has been to do what, something that is similar to what you do in a seismic pushover, to apply nodal loads at the story level, and these could be named as story loading discretization. An alternative approach that has been tested more recently is instead of applying loads just at the story level, you can apply loads along the columns. So a distribution of point loads along the columns that was found to provide a better estimation of the impact of the tsunami loads on the structure. And so important aspect to also understand here is that a portion of the loads that is, let's say, by which we discretize the overall tsunami force is going directly to the foundation. So what actually we are looking at here is the net tsunami force that is going to be resisted by the lateral force resisting system. At the start of my presentation, I mentioned that there are two main checks to be done according to the codes. One is the systemic check on the structural system, but the second one is on the structural components. So individual structural components are subjected to an enhanced tsunami force due to local effects around the elements. Also, if these structural elements are part of the lateral force resisting system, they should be tested against the combined effect of the systemic and structural component loads. That means that we need to come up with a sort of discretization that accounts for this second check. So this is what we have proposed, is to apply a distribution of point loads to the individual line of columns where we want to perform the structural component test check, and the remaining columns, and we apply to the remaining columns the remainder of the systemic tsunami force. These remaining columns can be, let's say, subjected to either point loads or distributed loads, as in this sketch, or point loads. And we have tested this all these assumptions and loading discretization in a structural element model in OpenSys. So I developed a 2D model of the structure. Due to time restraints, I'm not going to into the details of this modeling, but I want to highlight two things. First of all, a distributed plasticity that is here is essential approach for the modeling the structural elements is essential because we are applying a distribution of point loads along the elements. So this is something that you may not always assume in a seismic pushover analysis. But also there are shear reinforcement variation along the ground floor and upper story columns, and that also can play a role in the response of the structure to this tsunami loading. So let's now have a look at the results, and let's compare what you get by using the prescriptive systemic check. So what the AC7 tells you to do by using a simplified approach that essentially compares the applied tsunami force as calculated before, and the design strength of the structure, the seismic design strength of the structure, enhanced by to account for the typical overstrength. In this for the specific case of the building, the applied force, tsunami force, is smaller than the expected seismic strength. But what is interesting to note here is that this expected seismic strength, as defined by the code, is essentially based on the overstrength factor for the typology of frame. Here is a reinforced concrete frame, and the design base shear, so depending on its location and the gravity weight. So what happens when we apply instead a tsunami pushover analysis? Well, the overall, let's say, outcome is the same because in the black line here on the graph shows the tsunami pushover, which is much larger. What gets to, it's like the lateral strength is way larger than the tsunami load case to force, so the design event force by 40%. So that's okay. The lateral force resistance system should be sufficient to resist the tsunami force according to both checks. But to draw a fair comparison, we also have performed a seismic pushover analysis on the building, and we found that the actual strength of the structure is smaller than what was expected by the code. And generally speaking, this would identify an issue with this simplified check, because in this specific case, the simplified check by using the actual strength would fail the test. But more interestingly, is what Tiziana mentioned at the start of her introduction, was the behavior and the response of the structure under tsunami loading is significantly, is very much different from the seismic one, because we can see an increased stiffness and an increased lateral strength. But this is what we have observed in past studies as well, because this reflects the different nature of the way the seismic and tsunami loads impact the building. Usually, as Tiziana mentioned, the tsunami loads will be large at the base of the structure, whereas the seismic loads are going to be applied at each story up to the top of the structure, usually in magnitudes that are higher the upper stories. And this is what we get by using the story loads for the tsunami pushover. When we use the other assumption for the discretization of the overall systemic force, we can see a different strength, because the share of forces that goes into the foundation is much smaller under this assumption. But since the forces are applied mainly at the ground story columns, essentially these induce large shear forces, and therefore the occurrence of shear failure that is shown here as field markers along the curve. And that occurs earlier than the flexural yielding in the columns. Now, this distributed loading discretization can provide us an understanding what's happening when we apply an enhanced or let's say a considerable large forces at the columns, but does not reflect the component loading, because the component loading, as I showed earlier, is an enhanced force on the single individual column. So that is what we have done in the next check. So structural component, we do apply this enhanced loading on a single column and see what's happening. So essentially what the output of this check is that the structure needs to be strengthened, or the ground floor columns need to be strengthened to meet the collapse prevention performance level. But you can see the advantage probably that by using the tsunami pushover analysis, you could identify relatively in an effective way what are the elements that need to be strengthened. So we found also similar results by using either distributed and story loads to the remaining elements. And to conclude, we can say that this procedure offers a tool to practitioners to apply tsunami pushover analysis in the context of the AC7 standard. There's no currently guidance, so it's something that has been welcomed also by the subcommittee for the ACE, and actually we're trying to implement this into the commercial software Seismostruct to provide also a tool that can be used a bit more easily than in OpenSeas. But there are two main remarks I would like to make before concluding, is that it's clear from also these results that it's strongly recommended to perform nonlinear structural tsunami analysis instead of the simplified prescriptive check, because this is due to the complexity of relating the seismic and the tsunami lateral strength of a structure. And then when we look at the component loading, it's clear that having a tsunami pushover analysis can help to identify better what are the critical elements that need to be strengthened. And so that could provide also more economical design instead of redesigning all the structure to meet the design force by codes. And of course, this approach has for now included mainly the hydrodynamic forces as tsunami loads, but there are definitely other effects that are included in the AC7, and also we would like to include also in this tool. Marta will show in a few seconds how much is important to include other possible effects like vertical pressure or the failure of the Infields. So I will pass the stage to Marta.
Okay, thank you very much, Marco. And thank you, Valentina, and all the Second Committee for this invite for this presentation today. So I'm going to share my presentation. Can you see the screen? I hope so. Okay, so today I'm going to discuss, as Marco was saying, and also Tiziana, a methodology to assess the performance of existing structures under tsunami loading. So with Marco, we have seen what the AC7, which is the most updated code for the design of tsunami vertical structures, provisions. But in the framework of the assessment of existing structures that are not to be used as vertical evacuation buildings, we don't have any codes or guidelines. So basically, we need to define a methodology to assess this kind of structure, and this is of particular interest when we want to perform vulnerability of or loss assessment analysis. So I will start with a very brief introduction about the effects of tsunami on structures, and in particular, I will focus on hydrostat and horizontal and and uplift loads. As we know, tsunami are very complex phenomena, so they induce different kind of pressures and effects on existing structures. We have horizontal loading in the form of hydrodynamic or hydrostatic pressure that, of course, are impacting the exterior surface of the buildings, or are a function of the exterior envelope of the structure, and can have high magnitude at the bottom of the building. So basically, measured damage are concentrated at the ground story level in the form of flexural damage mechanisms, such as the soft story at the ground level, or shear failure of the ground story columns. But we have other kind of loads that are the vertical induced uplift loads induced by the tsunami on structures that usually are not included in common analysis when we assess the behavior of the structure, but they play an important role on the overall performance. So if we think to a building that has a very small opening ratio, or partitions that are able to sustain exterior enclosures that are able to sustain the tsunami flooding, in such a case, we will have high buoyancy on the building caused by the enclosed space, or the enclosed air inside the submerged building. And this enclosed space will develop uplift forces that will apply to the foundation of the building in this case. And these uplift loads combined with horizontal loads from hydrostatic or hydrodynamic pressure, who can lead sometimes to the global overturning of the structure, especially in the case of buildings with shallow foundation. But if the structure has exterior claddings that are not able to sustain the tsunami flooding, so tsunami load, so in such a case, we will have the failure of the exterior claddings, or for example, windows, if we have very high opening ratios, and the water will pass inside the building. So in such a case, we still have some enclosed spaces that are developed below the slabs, for example, in the forms of air pockets. We will have also a reduced weight of the submerged structural members. And if the water level rises over the first story slab, we will still have some enclosed space inside the submerged building that will cause uplift loads. In this case, these uplift loads are not acting on the foundation, but are acting on the first story slab of the structure. And in some cases, it was observed from past tsunami surveys that these uplift loads can also cause the uplift failure of the slab. And it was mainly observed in the case of precast concrete slabs. And then we have other kind of effects, such as the local scour, so the local soil erosion of the soil below the foundation, usually at corners of the buildings, and the debris impact caused by debris transported by the tsunami flow that can cause local damage to structural members, and in some cases also we can have the partial collapse of the structure. Given these different effects that tsunami flow generates on a structure, we can define a general framework for assessing the performance of existing structures under tsunami loads and effects. So given the hazard map, so we can define the tsunami parameters at the site of the building, we can compute the tsunami loading on the structure and on the foundation, and we can identify which is the governing failure mechanism for the structure and assess the capacity accordingly. So the methodology I'm going to present today is for the assessment of the superstructure behavior subjected to horizontal and uplift loads, under the assumption that this is the governing failure mechanism, and global overturning and the scour are not going to happen to this kind of structure. In detail, this methodology has been developed to estimate the vulnerability of existing buildings in the Mediterranean region, in particular in Italian coastal communities. And in our coast, usually existing structures are in the form of masonry buildings or reinforced concrete frame structures with unconfined masonry infill walls. And I will focus on this kind of structural typology. So if we think a reinforced concrete frame hit by a tsunami flow, the water pressure will act on the unconfined masonry walls that are responsible to transfer this load to the structural members. But of course, unconfined masonry infields are characterized by a very low out-of-plane capacity, so low capacity out of their plane, and they will probably fail under the hydrostatic and hydrodynamic pressure induced by the tsunami flow. So this kind of exterior claddings can be classified according to the AC7 as tsunami breakaway walls, so walls that will fail under the tsunami loading and will allow the free passage of water and waterborne debris inside the structure. We developed a procedure to incorporate the failure of these breakaway walls and also all the loads related to the water passing through the building, so in the forms of uplift loads acting on the interior slabs, in the general framework of the VDPO analysis that Marco has already presented. So this methodology that we call VDPO-BI, because it's a VDPO for breakaway infilled frame, is still an incremental analysis, and so for increasing inundation depth, simulates the actual distribution of loads on structural and non-structural components, accounting for the failure of the exterior claddings. So let's see some steps of the analysis. And at the beginning, so before the failure of the exterior claddings, the building is watertight, so the water is retained outside the structure, and so the load is acting only on exterior structural elements, and the horizontal lateral pressure is computed considering an impacting surface width that is equal to the entire base span of the structure. But when the failure of the ground story breakaway infields is reached, then the water is able to pass through the building. So loads are applied to both exterior and interior columns, and of course with a reduced width of impacting surface, considering that of course the failure of the infields will produce debris inside the structure. When the inundation depth rises over the first story slab, we will have the uplift loads acting on the slabs, and of course this will generate loads that are contrasting the gravity loads still applied to the structure, and it is a function. These are a function, especially of this enclosed space inside the building that is increasing with an increasing inundation depth, until the failure of the infills at the first story is achieved. This will allow the free passage of the water inside the second story, so inside all the first story. So both ground story and first story will be completely submerged, and of course it will change the distribution of horizontal and also uplift loads on structural members. So when we deal with breakaway infield frame, how can we compute the tributary width for computing and applying horizontal loads on the structural members? Well, minimum values of this tributary width can be adopted, accounting for the effect of damming debris. Since the tsunami flow is bringing with him a lot of the waterborne debris that in some cases can accumulate in front of the building, so increasing the impacting surface, so the surface exposed to the tsunami lateral pressure. So we can identify two limit conditions. One where a low debris impact, where a high probability of accumulation debris, like in this picture, is expected. So in such a case, we need to consider that the tributary width to be assigned to the exterior members should be higher than the one of interior columns. Conversely, in the case in which we have a low probability of accumulation of debris, of damming debris, we can assume a minimum tributary width that can be the same for both exterior and interior columns. Of course, the exact definition of this value, it depends on the kind of structure that we are considering, the connection between the masonry and the structure, and other details of the specific case study. The horizontal loads induced by tsunami can be applied on the structure in different distributions, and there is still no consensus about which distribution of horizontal load should be used during the performance assessment analysis. However, the selection of the load distribution is important. It's still an open issue, but it's important because it can affect the overall performance of the structure. Tsunami loads, of course, need to be combined with gravity loads, and we can follow the prescription of the AC7 for the design of structure. According to the AC7, we can use two different load combinations for gravity and tsunami loads. The first one is for buildings that are already evacuated before the tsunami comes. And it consists in 0.9, reducing the dead load by 0.9 and assuming 0 live loads. While the second load combination is less critical, since it considers both dead loads and live loads. So, of course, the choice of the load combination is also important because it affects the influence of the uplift loads on the overall structural performance. And if we look at a generic 3-story frame, and we look at the axial load variation in ground story columns during the analysis, so for increasing inundation depth, we can see that up to a certain point, the axial load in columns is constant because, of course, is given by the gravity loads. But when the uplift loads are applied to the slabs or are acting on the slab due to the buoyancy, we will have a progressive reduction of axial load. And this the enclosed space inside the upper story governs this load reduction. So it can lead to very significant reduction in axial load for ground story columns, and of course related reduction in flexural and shear capacity. This up to the failure of the first story infields. So when the failure of the infields at that story is reached, the water will pass inside the building, pass through the building. So this component of enclosed space will disappear, and so we will have a release for the structure. And this effect of uplift load is more significant in the case of low-rise frames. So if we compare the axial load variation with low-rise, mid-rise, and high-rise frames, we can see that actually the axial load reduction is still important when we increase the number of stories. And this is, of course, because it's increasing the initial axial load given by the gravity loads. Because the uplift loads caused by the tsunami are actually the same for the three cases. So now let's see an application of the methodology. So we will apply the VDPO BI for 3-story RC frame designed for gravity loads only. And for this application of the VDPO BI, I'm considering the load combination 1, so the building is evacuated, and I'm assuming a negligible damming debris accumulation at the side of the building, so I'm not overloading the exterior column. Regarding the distribution of horizontal load, I'm using an empirical model developed by Key et al. In 2014 with a triangular distribution, and a Ford number. The Ford number of for the tsunami characterization is assumed equal to 1. So for this first application, we are comparing and seeing the difference in structural performance of a structure with non-breakaway infields, also watertight building, and a structure with breakaway infield walls, assuming that the out-of-plane failure of the infields will happen when the inundation depth achieves 1 meter from the bottom of the infield. So in the blue line represent the capacity curve in terms of base shear and maximum inundation depth, so tsunami inundation depth for the watertight case, while the black line represent the behavior, the performance of the buildings when the effect of the breakaway infields and the uplift loads are considered. So of course, the failure of the breakaway infields changes the global and also the local behavior of the structure. And this is particularly visible in terms of base shear for the building. And the thing that we can notice is that even though for both the two combination, the shear failure of the exterior columns of column 1 is still the predominant mechanism. So even though we are considering the failure of the infills, the shear failure of the column is the mechanism that will be activated first with respect to the first yielding of the columns. So if we look more in detail about the local performance of the structural components, and in particular, we look at the moment rotation relationship at the bottom section of the ground story columns. We can see that in the case of watertight frames, so case 1, we will have a high deformation at the bottom of column 1, which is the column where all the loads are applied in the watertight configuration, while the other members are still in elastic field up to the achievement of a mechanism, so the activation of all the plastic hinges for the soft story. Conversely, in the case of breakaway infield, so in case 2, all the plastic hinges develop almost simultaneously in ground story columns. And this is most, of course, because the load is applied, is the same load applied to all columns during the after the failure of the breakaway walls. In terms of brittle mechanism, the shear demand to the exterior column, so to column 1, this is the shear demand in the case of watertight buildings, so in case 1, while the black line is the case of building with breakaway infields. So we can see that at 1 meter, when the inundation depth achieves 1 meter, so we have the failure of the breakaway walls, and then we have a sudden reduction of the shear force acting on the exterior columns. And of course, this we can, in some cases, can postpone the shear failure. So for the specific case, looking at the range of shear capacity as a function of the axial load variation, the failure of the breakaway walls will postpone the shear failure mechanism. Of course, it depends on the capacity of the members of the columns and also on the out-of-plane capacity of the exterior claddings. And finally, to point out how relevant are the uplift loads on the overall structural performance, the analysis, the same analysis of the VDP of EI has been conducted now neglecting the uplift loads. So the uplift loads, if you look at the local behavior of structural members, and in particular we look at the axial load reduction in ground story columns for this particular case study, we can see that there is a strong axial load reduction up to 0 values in both interior and exterior columns. And of course, this is reflected in the moment rotation capacity of base section of ground story columns. So this is the behavior, the moment resisting capacity of, in the case of when uplift loads are considered, and this one, HP2, is when we are not considering, we are neglecting the effect of uplift load. So there is a very strong difference in terms of moment resisting capacity. And of course, this is reflected in the overall global performance of the structure. So in terms of capacity curves, where the black line is always the capacity curve as considering the uplift loads, and the red line is the capacity curve under the assumption of no uplift loads acting on the structure. And it is clear that neglecting this kind of tsunami-induced loads can lead to a strong overestimation of the actual capacity of the structure, both in terms of base shear and also maximum inundation that the building can sustain during a tsunami inundation. So to conclude, we have seen that we don't have any guideline for the assessment of existing structures. So for assessing the behavior of existing reinforced concrete frames with measuring fields, we developed this variable depth pushover for frames with breakaway infields, the VDPO-BI. And the application of this methodology has shown that the effect of the breakaway infield can strongly affect the global and local performance of the structure. So the use of this kind of approach is recommended when you are dealing with frames, not only reinforced concrete, but in general frames with exterior claddings that can be classified as breakaway walls according to the AC7. And we have also seen how much the uplift loads induced by tsunami are affecting the overall and global performance of the structure, and also, of course, the achievement of local mechanisms such as shear failure. So neglecting this kind of component in both design and assessment can be really dangerous. So this needs to be included in all analysis. And finally, we have also shown that for this kind of structure, with or without considering the effect of breakaway infield walls, the predominant failure mechanism is governed by the shear failure of ground story columns. Of course, needs to be further investigated also with experimental validation. And thank you very much for your attention, and if you have any question.
Thank you very much. Can you hear me fine?
Yes, very well. Mm-hmm.
Okay.
I really cannot see the chat box.
Me neither.
Okay.
Okay, I think there are a couple of questions.
Okay.
One is from Roberto Gentile. Would it make sense to weaken the infields as a retrofit strategy? And actually, Tiziana replied, yes, it's weakening the infields can be effective. Maybe, I don't know if Marta wants to say a little bit more on this.
Yes, definitely weakening the infields can reduce the load acting on the structure. So if we are, since we are not, we want to preserve the structural integrity and avoid the formation of debris, because of course the collapse of a structure will also become a debris for other structures. So in such a case, yes, we can suggest to weaken the infield walls. And of course, we are allowing that this building is not used as evacuation building, and all the contents inside the building can be lost. So in this sense, we can accept this kind of weakening strategy as a strengthening strategy for the structure.
And there is another question by Fernando Gutierrez.
Thanks, Marta.
You're welcome.
It's about assessment of existing structures. Question is, if we assess that the structure is not does not comply with, let's say, with the expected forces applied to the structure, then what could be the recommended measures to reduce the demands on the structure, or is there retrofit the only path of option?
Well, as for me,
I think, yeah, you presented the more like the assessment side of the.
Well, basically, up today, it's not easy to define strengthening solution for tsunami. But yes, if the structure is not able to comply with the demand, we can either try this approach, weakening the building, and so in this way we are reducing the loads acting on the structure. Or we can strengthen the structure, for instance, if we observe, depending on the failure mode. So if we find that the shear failure is the governing mechanism, we can strengthen for shear based the ground story of the building. So in general, strengthening the ground story can be a solution. But there are also more general approaches that can be also adopted. I don't know if Tiziana wants to. I see that she's.
Yeah, I mean, I think it depends on the circumstance. It depends on the actual building, but it would be a combination of reducing the loading on the building by, for example, allowing breakaway infills, or indeed blowout slabs. In theory, we could see, but that by itself might not solve the problem. It might solve the problem because you're reducing the loading. but you may have to strengthen the elements of the structure as well, in particular with shear, shear strengthening. But it's not yet. It's the next stage in our work, I think, is looking at potential strengthening options, and also looking at, if you're providing breakaway walls, not creating additional debris. So how do we have a wall breakaway without it causing hazard to life, basically. So there are issues like that we still have to resolve.
Mm-hmm. I think there are a couple of questions by Chris. Lyle is, do you use standard water density for the loading? I believe I can answer here because the AC7 provides a guidance on this. Essentially, we apply a 10% increase in the water density. And the second question is, do you consider the retained weight of water left on the first story slab when the water recedes? What I can say, maybe Marta can add something on this, and Tiziana. From a design point of view, for now we have considered mostly the inflow, let's say, stage of the tsunami inundation. So we have not still accounted for what's happening when you have the receding flow in terms of cumulative effects. And definitely, maybe I will let Marta explain more in detail about consideration of the weight of the water left on the first story slab when the water recedes.
Yeah, actually, we are not still considering this. I mean, we discussed it a bit with Tiziana, Marta, and also with Ian Robertson from University of Hawaii. So basically, during the inflow, we are not having this problem, so we don't have this water retained inside the building. But during the when the water is recessing, we can still have some water inside the structure that will have as a surcharge for the building. So actually, it can be efficient because we are increasing the gravity loads for some cases, but for others, like for example for steel structure, it could be dangerous. So we are now working also on this to include in the VDPO2 AC analysis that Marco developed and presented going to include also this effect. But it can be, it should be included.
I think there are no further questions, unless someone wants to maybe switch on the mic and ask directly.
Exactly. Go ahead.
Sorry, Valentina.
No, thanks. Thanks. So no more questions. So I'd like to thank very much Professor Tiziana Rossetto, Marco, and Marta for your contribution. It was a very interesting topic. And before leaving, I want to remind you that there are still 3 spots available to join Young SECED and to be part of the group. So if you want to put yourself forward, please go ahead. Don't forget that you must be a member of SECED first before nominating yourself. And until the 31st of October, you have the chance to win £500 by taking part to the logo competition. And we are seeking new ideas to give a brand new logo to the society. So please consider also this option. Go and visit our webpage. So thank you very much. Thanks to the speakers and to all the people that have attended the meeting. And stay safe and see you soon.
Thank you. Thank you.
Bye.
Bye.
Bye-bye.
Bye, thank you.